Welcome to Einsteinium theoretical physics. Let's understand around us. In this video, we will see the rise of Newtonian physics, Part 1. Newtonian physics was a pantheon of science. It was a combination of concepts and frameworks that resulting from a long process of discoveries and synthesis of ideas that lasted for 2,000 years. The standard metaphor for Newton's universe emphasizes its philosophical implications. A world that was orderly, predictable, and understood. Euclid of Alexandria, a Greek mathematician, active as a geometer and logician. He was considered the father of geometry, chiefly known for the Elements Treatise, which established the foundations of geometry that largely dominated the field until the early 19th century. His system, now referred to as Euclidean geometry, also known as the geometry of plane figures. Euclid described different terms of geometry such as point, line, surface, and more in his book. The Elements is often considered after the Bible as the most frequently translated, published, and studied book in the Western world's history. In the Elements, Euclid collected, organized, and proved geometric ideas that were already used as applied techniques. He gave definitions, postulates, and axioms. He called axioms as common notions, a self-evident truth. Euclid described a point based on the idea that a point has a position, but no magnitude, which means that a point has no breadth or length. A point is dimensionless. When a point moves freely, and if we trace its path, we get a curved line. Same when moves without changing the direction, we get a straight line. Thus, a line is generated when a point moves. A line has length but no breadth. It has one dimension. The distance between the points A and B gives the length of that line segment AB. So a line segment has a definite length. A line starts from one point and it extends endlessly on the other side. It is called a ray. When two lines move apart, they form a plane surface. A plane surface has two dimensions, length and breadth. Some of Euclid's general axioms were: 1. Things equal to same things are equal. If A equal to X and B equal to X, then A equal to B too. If equals are added to equals, the wholes are equal. If A equal to B and C equal to D, then A plus B equal to C plus D 3. If equals are subtracted from equals, the remainders are equal. If A equal to B and C equal to D, then A minus B equal to C minus D 4. Things that coincide with one another are equal. Congruent triangles can superimpose each other. 5. The whole is greater than the part. 6. Things which are double or half of the same thing are equal. If A equal to 2x and A equal to 2y, then x equal to y, and if x equal to half A and y equal to half A, then x equal to y. These axioms are used in many mathematical proofs, especially in geometry. Some of the Euclidean geometry rules. 1. The line drawn from the center of a circle perpendicular to a chord bisects the chord. 2. The perpendicular bisector of a chord passes through the center of the circle. 3. The angle subtended by an arc at the center of a circle is double the size of the angle subtended by the same arc at the circle. 4. Angles subtended by a chord of the circle on the same side of the chord are equal. 5. A tangent to a circle is perpendicular to the radius drawn to the point of contact. Elements contain formulas for calculating the volumes of solids such as cones, pyramids, and cylinders. Also proofs about geometric series, perfect numbers, and primes, and the algorithms for finding the greatest common divisor and least common multiple of two numbers. A proof and generalization of Pythagoras' theorem, and proof that there are an infinite number of Pythagorean triples, and a final definitive proof that there can be only 5 possible regular Platonic solids, which we saw in our previous video about Plato. Euclid's proof of Pythagoras' theorem demonstrates if a line is drawn from the right angle, perpendicular to the hypotenuse, and down through the square, that square will split into 2 rectangles, each having the same area as the squares on the other 2 sides. Aristarchus of Samos, one of the believers in a sun-centered universe. He presented the first known heliocentric model that placed the sun at the center of the known universe, with the Earth revolving around the sun once a year and rotating about its axis once a day. The only surviving work of Aristarchus on the sizes and distances of the Sun and Moon. This work calculates the sizes of the Sun and Moon, as well as their distances from the Earth in terms of Earth's radius. His observations were based on the apparent size of the Sun and the Moon in the sky, the size of the Earth's shadow in relation to the Moon during a lunar eclipse. The angular distance between the Sun and Moon during a half moon is 87 degrees. Aristarchus began with the premise that during a half moon, the Moon forms a right triangle with the Sun and Earth. By observing the angle between the Sun and Moon, theta, the ratio of the distances to the Sun and Moon could be deduced. He determined the theta to be 87 degrees by only using geometrical analysis, modern-day value being 89.853 degrees. That is, the Sun is between 18 and 20 times farther away from Earth than the Moon is, and the Sun must therefore be 18 to 20 times larger. Using his methods, modern-day calculation of right-angled triangle reveals cos theta equals dm over ds, the distances to Moon and Sun from Earth. The adjacent side by hypotenuse, rearranging gives ds over dm as 390, shows that Sun is roughly 390 times further away from us than Moon. Aristarchus found the Moon's diameter to be between 0.32 to 0.40 times the diameter of Earth, and the Sun's diameter to be between 6.3 to 7.2 times the diameter of Earth radius. It was calculated on solar eclipse, when two right-angled triangles are formed. Then the ratio of the distances and radiuses are equal, which equals to 390 as before, showing that diameter of Sun to Moon is 390. Modern-day calculations show the diameters of the Moon and the Sun, compared with that of Earth, are 3.6 and 109 respectively. Another observation was based on lunar eclipse when Earth casts shadow on the Moon. The diameter of Earth's shadow is twice the diameter of the Moon. Modern-day values shows that it is 2.6 times that of Moon. It is calculated as R shadow is the cast shadow at Moon's location. RS and RE are radiuses of Sun and Earth. DS and DM are distances from Earth to Sun and Moon. When the two right-angled triangles are formed, the distances ratio is equal to the ratio of heights, which is RS minus RE, and RE minus R shadow respectively. This is same as ratio of radiuses as seen before. Now rearranging this by moving RS to one side gives this, upon simplifying and rearranging gives this. Using Aristarchus' idea, and based on the modern-day value, replacing R shadow over RM by 2.6 gives this expression. Now taking RE over RM as common and rearranging gives this, based on previous calculation, RM over RS can be written as 1 over 390, which is roughly 3.6. Now rearranging these expressions tells us the radius of the Earth is 3.6 times the radius of Moon. Now rearranging the same expression in another way by taking RE over RS as common, rearranging and replacing by 390 gives the radius of the Sun is 109 times the radius of Earth. Aristarchus gave measurements to find the distance to the Moon from Earth based on full moon observations. He said angle formed between the two lines from observer on the Earth that connect to the full diameter of the Moon, capital DM. The distance of small dm can be measured. The modern-day value is 0.519 degrees. The ratio of the angle theta over the full orbit of 360 degrees is equal to ratio of diameter of Moon to the circumference of the orbital circle, which is 2 pi times radius, which is dm. Solving for diameter to distance of the Moon gives roughly 0.009. This can be used to determine the distance of the Sun and Moon in terms of diameter of the Earth. To calculate that, we can start from distance to Sun over diameter of Earth. Rewriting in terms of diameter of Sun gives this, from previous calculation, we know ratio of distances of Sun to Moon is equal to ratio of its diameters. Rearranging, we get ratios of distance to diameter. Replacing that here gives this expression. We know these two ratios, applying that gives roughly 12,000. Which says that the Sun is approximately 12,000 Earth diameters away. To find distance of the Moon to the diameter of the Earth, we can use the same method. Now, rewriting in terms of diameter of the Moon gives this expression. Applying the known values gives roughly 30.9, which says that the Moon is approximately 30.9 Earth diameters away. Archimedes of Syracuse, the most famous mathematician and inventor, referred to as the father of mathematical physics, founder of theoretical mechanics. He derived the first calculation of pi using the method of exhaustion from Eudoxus and Euclid's proposition. On his treatise, Measurement of the Circle, he approximated the circle using pi value. The ratio of the circumference to the diameter of a circle is shown to lie between the limits of 223 by 71 and 22 by 7. In his another treatise, On the Sphere and Cylinder, he proves the surface area of any sphere of radius r is 4 times that of its greatest circle. Modern notation is s equals sine 4 pi r squared, and the volume of a sphere is 2/3 that of the cylinder in which it is inscribed. This is same for surface area. Another surviving work of Archimedes, On Conoids and Spheroids, deals with determining the volumes of the segments of solids such as circle, ellipse, parabola, or hyperbola. These are formed by the revolution of a conic section about its axis. In modern terms, those are problems of integral calculus. Conoids are the conic sections revolved around one of their axes. A circle becomes a sphere. An ellipse becomes an ellipsoid of revolution, also known as a spheroid. A parabola becomes a paraboloid of revolution, and a hyperbola becomes a hyperboloid of revolution. On the Equilibrium of Planes is another treatise by Archimedes in 2 books. The first book contains a proof for law of the lever and culminates with propositions on the center of gravity of planes, and second book examines the centers of gravity of parabolic segments. One example of postulates is that equal planes at equal distances are in equilibrium, and equal planes at unequal distances are not in equilibrium, but inclined towards the plane which is at the greater distance. Simply, magnitudes are in equilibrium at distances reciprocally proportional to their weights. Archimedes' quadrature of the parabola demonstrates that the area of any segment of a parabola is 4/3 the area of the triangle having the same base and height as that segment. That is again a problem in integral calculus. He calculated based on the decomposition of a parabolic segment into infinitely many triangles. Assuming the blue triangle has area of 1, each green triangle is 1/8 the area of the blue triangle. Each yellow triangle is 1/8 the area of a green triangle, and so forth. The total area under the parabola is calculated as, and sum of this geometric series will be 4/3. The sand reckoner is a work by Archimedes at that time. Myriad represents 10,000 in the Greek number system. He proposes powers of myriad as myriad myriads, which is 10 power 8. He called that as first order of base 100 million, and called 10 power 8 itself the unit of the second order. Multiples of this unit then became the second order, up to this unit taken a myriad times, which is 10 power 16. This became the unit of the third order, whose multiples were the third order, and so on. Archimedes continued, and the largest number in this series is 10 power 8 power 10 power 8, which he called the order of first period. With this value as base, which is unit of second period, he continued to get the order of second period, and so on. He continued to get the last number of this series by anyone's reckoning as 1 followed by 8 billion billions of zeros, and in modern notation, it is given as 8 times 10 power 63. He argues in this work that this number is large enough to count the number of grains of sand which could be fitted into the universe, which is the reason it is called the sand reckoner. He also discovered and proved the law of exponents, 10 power a times 10 power b equals 10 power a plus b, necessary to manipulate the powers of 10. Archimedes took Aristarchus' heliocentric model of universe, as it was not stated how far the stars were from the Earth. He made the following assumptions. 1. The universe was spherical. 2. The ratio of the diameter of the universe to the diameter of the orbit of the Earth around the Sun equals to the ratio of the diameter of the orbit of the Earth around the Sun to the diameter of the Earth. 3. The perimeter of the Earth was no bigger than 300 myriad stadia. 4. The Moon was no larger than the Earth, and that the Sun was no more than 30 times larger than the Moon. 5. The angular diameter of the Sun, as seen from the Earth, was greater than 1/200 of a right angle. He then concluded that the diameter of the universe was no more than 10 power 14 stadia, and that it would require no more than 10 power 63 grains of sand to fill it. On floating bodies, the first known work on hydrostatics, known as Archimedes' principle, also known as physical law of buoyancy. King Hiram II gave a goldsmith a particular amount of gold to melt down and make into a crown. When the crown was made and returned to the king was suspicious that the goldsmith had stolen some gold and replaced it with some silver. The king turned to Archimedes for help. Archimedes happened to go to bath on a tub. On getting into the tub, he observed that water ran out over the tub. He realized that the water overflown by his body was equal to the weight of his body. Knowing that gold was heavier than other metals, the goldsmith could have substituted in. Archimedes had his method to determine that the crown was not pure gold. Forgetting that he was undressed, he went running naked down the streets from his home to the king, shouting, "Eureka!" His principle shows the buoyant force and displacement of fluid. His proposition was, any object totally or partially immersed in a fluid or liquid is buoyed up by a force equal to the weight of the fluid displaced by the object. The weight of the displaced fluid is directly proportional to the volume of the displaced fluid. The weight of the object in the fluid is reduced because of the buoyant force acting on it upwards. In simple terms, the principle states that the buoyant force Fb on an object is equal to the weight of the fluid displaced by the object, or the density of the fluid multiplied by the submerged volume and the gravity. The Archimedes principle is a very useful and a versatile tool to measure the volume of irregular objects. This principle describes how ships float, submarines dive, hot air balloons fly, and many other examples. The Archimedes principle is also used in a large variety of scientific research subjects, including medical, engineering, entomology, engineering, and geology. The Archimedes screw is a device used for transferring water from a low-lying body of water into irrigation ditches. Archimedes gave an explanation about the principle of lever. He said, "Give me a place to stand on, and I will move the earth." Archimedes' war machines. Syracuse, his hometown on the island of Sicily in the Mediterranean, was constantly under the threat of attack by the Romans. When 60 Roman ships under the command of Marcus Claudius Marcellus laid siege to the city in 214 BC, Archimedes used his knowledge of physics to fend off Roman ships approaching the fortified walls of Syracuse. He invented a giant iron claw, operated by virtually the entire population of Syracuse from inside the city's walls. Outside, the claw was capable of picking up entire Roman ships and plunging them into the sea. He used catapults and heavy timbers to hurl objects at the ships in the distance. Archimedes' heat ray, or death ray, is a device that he purported to have used to burn the attacking Roman ships. He used multiple mirrors acting collectively as a parabolic reflector of the sun to burn the ships. Modern engineers are less sure about the concept of death ray. Newtonian mechanics was a collective work of many mathematicians, philosophers, and physicists. We will continue to see the rise of Newtonian physics in the next coming videos. Let our gravity attract you. Stay with us. Thank you.